So, I mean, you probably heard here when you get a bunch of new features in the latest Rust release, comes in the big blog posts, and usually one or two people from the Rust community will make a big summary of the actually important things. And we also have a lot of stuff in the pipeline. Some pipelines are rather long, some pipelines are a bit shorter. So rather long can mean probably the next 5 years, I hope. Otherwise, some things are probably the next 6 months. So this is pretty random, but I'm just going to make a big dump of stuff that's unstable and that we might get sometime in the near or further future. I would if my keyboard actually did that. Lots of acronyms. We love acronyms in the Rust project. This is called TATE. TATE is type alias infiltrate. Infiltrate is stuff that you put at the end of your functions when you don't actually want to specify what type you're returning. It's also a thing that async functions return. They return effectively in impl future. You don't actually know what type it returns, but you know at least it's some kind of future, and you can poll the future because that's all you actually care about with the future. There's a missing piece in all of this, and that's you cannot actually name those return types. So you have a function that returns an impl iterator that returns an impl future, and you may want to like pass it somewhere, store it in a struct field. I don't know what you want to do with it. There's like lots of use cases for these, and the problem is you just can't. Well, you could just box it, make it a dun iterator, a dun future, and then store it, of course. But just storing the plain object of a type that you don't know, like you have to write the type down. Otherwise, you can't make the field have to have that type name. So the solution is TATE. It's basically you're using infiltrate inside a type alias. That's why it's called type alias infiltrate. Well, let's look at how this actually does. Here I create an iterator. Impl iterator, item, user. You get lots of user queues. You don't know how many. It's not exact size iterator. It's not double-ended iterator. It's just iterator. Pretty simple. You could add more types there. You could do impl iterator plus double-ended iterator if you wanted. So everything works here as normal. But the new thing is that you can actually put it in a type alias. And now that you have a type alias, cool thing is you can use them anywhere. You just stick them somewhere. Like normally return type is the boring piece. But then the cool piece is you can make it an argument. And this argument is the same type. This is not an argument precision infiltrate. This is not a generic parameter. This is just another usage of this type. And you could put it in a field and just store a value of that type in that field and pass it around. If your thing is really big, you could still box it, but you don't need to do it because you know the actual type. And you don't need to have new tables. You don't need to have any indirection. You just literally call the object directly. And few things of that type. Yeah.
So does it mean that you have basically every time you use this type, does it influence what can be placed inside the type? Because like one of the uses defines what is actually the specific type.
I get to that in a second. So this is, we're still in the using side. When you're using a value of that type, all you know is those bounds, similar to how a dun would work. With a dun iterator, all you would know it's an iterator called the next method and the various combinators that exist for it. But with this one, you don't know anything additional. It's similar to a generic parameter where you also don't know anything additional. But in this case, it's a concrete type. This is not a function that at the end of the time, at the end of compilation will get instantiated with different types. This is a function, it's a normal function with one concrete type. And inside, you can use this iterator as normal in for loops, or just calling .next on it, or feeding it to a random thing that needs an iterator, and just works fine. The problem is, if at some point you actually want to specify what the actual type behind the thing is, you need some way to tell the compiler about that, because in this case, for example, where you want to return an iterator, that might be the function where you want to declare actually like, oh, this is an std iter once, or this is a back and then into iterator or something like that, that you don't actually know where the iterator comes from, but at some point you need to know. The compiler needs to know. It cannot create a type that it doesn't know about. And the thing is, it needs to create it within this crate. So you can't declare this type alias and then 2 crates down be like, hey, I'm going to now say like the actual type is a specific type, because then 2 crates could do that. And now you have 2 types for 1 type. Yeah, it's not going to go well. So in this case, what we have is a temporary syntax right now that we not sure if we're going to stabilize it, but basically there's an attribute that just says like define opaque, and then you specify like attribute define opaque my iterator, and then this function is allowed to actually define that one. And this is very powerful because you can do this anywhere in your crate. Anywhere in your crate where you have access to the name of this type. So if it's not public, then you can't access it. But as long as you can access that type, you can declare it. So it doesn't have to be in the same module. It can be completely somewhere else in the same crate. And that allows you to, for example, make this declaration at the top of your crate public for everybody to use who uses your crate. And the only definition can be somewhere completely in depth of your crate. It doesn't like, they don't have to be connected in any specific way except by that one attribute. And it gets funnier because you can use the attribute multiple times. And the compiler will ensure that all the usages are actually resulting in the same final type. But when it does that, you have to be a little bit careful because the compiler treats this as a concrete type and as a different type from the actual type that you put in there. So if you know, for example, this would the hidden type of this would be my struct foo. Well, it doesn't matter if you know it, as long as you can even try to tell the compiler about that. Unless you use the attribute, the define opaque attribute, the compiler will never combine these types. And like, no matter how much knowledge you have about the background, the only way to get out of this would be then transmuting stuff around or something like that. But like, the compiler protects you at all view sites and tells you what you have to do. But this means you also give up some control to the compiler because in order to do that, it needs to protect you from stuff from doing wrong. So yeah, powerful feature. You can literally implement type off with this feature. Please don't. No, you can do it in some cases, but the type off thing where you have like you say type off an expression and you get the type out of that. You can implement that with type infiltrate in very hacky ways, and it works. And it's probably going to make your compile time tank if you use it too much. So, but other than that, if you have a really important use case for it, well, use it. Have fun. Yes.
So just I understood that correctly. Also put actually such a type alias with a type which is not nameable.
Yeah.
Like a future.
Yes, a future, a closure, whatever. It doesn't have to actually have a type that you can name. And now you can name it because now you gave it a name, an alias, but it's still a name. And you can use multiple infiltrates in the same tab alias. And they are like independent ones. You can have a tuple of multiple infiltrates. That's totally fine. Yeah.
But I mean, can I make a vector of like 3 different impl iterator things? Because there's a different size, right?
They're different types. They're completely different types. So when you declare your vector in a square bigger, smaller signs, brackets, you have to specify a type, and you can specify a type list infiltrate. That's no problem, but you can't specify different ones because they're different ones.
But if I say like if I make 2 aliases and they are both impl iterator item u32,
yes,
they can have like A and B names, and I make, but they are kind of okay. I can never. There's no situation where I can make 2 functions that return some kind of impl iterator, and then the result of this I put in the vector.
So even if the hidden type behind those type aliases is the same, the compiler will not notice. The compiler will see those type aliases and say these are different types. Like the opposite of the image of this is the same image corporate thing. Like the compiler will say these are different types. You cannot merge them in any way. The thing is, once you get to code gen, once you actually generate machine code, the compiler's like, oh, I just look at what the actual type is. I don't care. Yeah, until then, it's non-existent. So if you're writing a code gen backend, you don't actually care. Those types don't exist for you. RTM, not an acronym. Return type notation. Wait, didn't we just say like we were naming like return types? Well, yeah, but this one doesn't quite do that. So return type notation is a way to specify bounds on the return types of functions. So for example, you have an async function and you're calling that somewhere, and you want to say that the future you get back is send. So with the trait has async and true, and now you have a generic parameter that's foo, and you can say the function foo has to return send. The syntax is whatever it is. I don't actually care because it's a funny feature. It's pretty useful. If you come up with a better syntax, you can complain on the appropriate issues. But there have been lots of syntax backshading on this, and this is literally the best we have so far. So maybe check if somebody didn't have your syntax before, because
Please don't post.
we just started a lot of syntaxes. Yeah, so this is short, and that gets to the point. You say the function returns. If you call the function, you get a send. In this case, this is useful because before, when you had a function like this, you couldn't actually put this into a Tokyo spawn because Tokyo spawn accepts something to be sent. And an async function in a trait, it doesn't say whether the thing is sent. It doesn't say whether the actual implementation returns something that is sent. You would have to turn this into an fn foo arrow impl future plus send, which is quite a mouthful, and is also now everybody needs to have a send future that implements your trait, which might not be what you want. So this thing allows you to make a choice depending on the implementer of your trait. Somebody implements your trait with a future that is sent, then they can put it in there. Somebody implements it with a future that's not sent, they cannot put it in there. Yeah.
It's just new syntax to refer to the return type of the thing foo.
Yeah.
So like, how does this sugar again, like a type that is like the output of the foo future is a type.
The
And the, like,
yeah,
is syntax just another way to refer to the type instead of the associate?
Yes. Yes. With type simple trait, we would not need this feature. But if we wouldn't have this feature and we had type simple trait, this short thing would be like this long and contain like all kinds of projections and all kinds of other traits. And you couldn't write it succinctly. And of course, you can add macros and make it a bit simpler and so on. But yeah, we just added the subsyntax there. It's also really useful when you get to more complex things like async event. Because async functions, the async event trait technically has two return types. It has the actual return type of your async function that you put in the arrow, and it has the future type. And then you would be like, which type do I actually want? And then it would get really complex. And this one just always gives you the right thing. Big break, completely different thing. Pattern types. I love talking about pattern types because I'm working on them a lot. I had a whole talk about them at FOSDEM if you want to actually see more details, because now I'm just going to make literally just one slide. Pattern types are something, the type analysis are right here, but you can specify a U32 limited to a certain range of numbers. And it's funnier than that because this on this side, it is a pattern. And if you remember your pattern syntax and matches, you can also make a pipe there and specify like, or it's 500 to 600. And you can do arbitrary things there that one. You can create huge patterns, put this thing in type alias, and now you have to call the type that is restricted to a specific range of numbers. And of course, it's not limited to numbers, because anything you could put, you can do the pattern, you are allowed to do here. Any type works here, as long as the pattern here matches the type that is there. Yes.
this then it says runtime checks or how does it?
No. So
Check
this
the
is only
compile time.
this is only the type declaration. There is literally no logic in the compiler language so far that does anything with this except declare this type and create niches. So this type is literally only valid in this range. If you transmute a number outside of this range to this type, instant UV.
So when you say niches, does that mean it also makes use of niche options?
Yes. You can put, this is a U32. You can put 2 to the 31 plus a lot of options around this type, and it will still be the same size as the U32.
How would it look to get an inhabitant of that file? So if you
How do you would look to get an
have so
inhabitant?
yeah, like if I want to have a value that inhabits this type, like I
So
can give a constant, but is there any other way to?
right. So we have a version that works for unsigned integers right now. Very limited. Where you can specify just a literal.
Yeah.
And the literals will just work. So if you specify like 50, it will just work. If you specify 200, it will compile error because it's a type mismatch, because that doesn't work. Negative numbers don't work yet. This is not intended as a feature that we are putting out to the public really yet, but it's a feature that we're using to change the internal representation of like non-zero types, non-null, and so on. But the moment everything the standard library and the compiler has settled down around this feature, which I'm expecting sometime next 2 months, then we're restarting the RFC that is open for these, because there's an open RFC for these, making them actually useful and giving them all the nice stuff that you want. And you'll get try from, you get from implementations to convert, like you've got all the convenient things. There'll probably be a bunch of coercions, so you can just always turn the value of this type into U32 without having to do anything, like just assign it, it'll work. Yeah, so I'm gonna go through questions first before I talk more.
What are the ideas to make this useful? I mean, if I like read a number from disk and then assign it to a value of this type, it's supposed to be always runtime checked with try problem.
Right. If you're reading from disk, you obviously need to run and check it. But the thing is, once you've checked it, then you have this type, and then you can pass that to type around, and you know for sure it's going to stay in this range.
Does the subtyping work native?
We don't know. We don't know yet what we're going to do about that.
Okay.
So that's a complex topic, because at some point you get to a point where it's like U32 is 0 to U32 max. Is that different from U32?
Yeah.
And there's so many questions there, which is basically like we're going to put that to the future and we're going to figure it out.
Okay, so my first question was also whether this is effectively subtyping in the sense that lifetime is set like a subtyping mechanism.
Not yet.
Okay, but and the second question is, there is like the old idea, which I think has been abandoned for some time, called variant types, where you basically say, okay, each variant of an enum is also a type. Used. The general version of this concept replace or substitute this.
100%.
Great.
Because the problem with variant types was we didn't actually know what we wanted from them. Like everybody who was talking about variant types had a different image in their head about what they wanted. These are fairly straightforward because they're always the size of the base type. There's no ambiguity here. All you're doing is restricting the niches around that. And that's a pretty straightforward thing that we can implement. And it's a little bit simpler than variant types in the sense that when you have an option of this, you get the niche optimization that this is put in the option. But the option itself isn't optimized any further. Like, if you want that, you would have to write option of something here and then optimize it with a pattern here.
Can I override the behavior that happens after rushing through the upper or lower bounds?
There is no behavior because you cannot crash through them because there's no operations implemented on these types. Does that succinctly badly answer your question? Or doing more context?
Happens after someone would, let's say, add some value beyond the upper bound, and then
Initially, we're not going to do that, but once these types are out there, you can write these, like write wrappers around these and crates. So initially we're gonna rely on the whole new type stuff because it's not always clear what kind of operations you would want on that. As like addition makes sense, but in this case, when you add an U32 of that to another one of these, you want the resulting range to be 0 to 200. That's possible. Or did you want to keep it in this range 0 to 100?
Well, if it's also a type, it must be bound to the lower number bound.
Right. But if you're adding one U32 is 0 to 100 to another one, the result could be inside 0 to 200 without having to do any bounds checking. That's one thing people could want. The other thing people could want would be overflow checks to ensure it doesn't go over 100. And to completely sidestep this issue, we're going to go basically the route we did with wrapping and like we have these wrapper types. Basically, we're going to add wrapper types around these that give you the behavior that you're expecting, including either increasing the range or doing bounce checks and giving you all the control of what you actually want instead of stuffing everything into this one type that is actually just a representation change.
I think my question is pretty much starting from the same point. From a type system perspective, I think it's similar to climate times, but a little bit reduced. There's an interesting paper by Wu and Yalla, I think. There's for Rust, basically for the climate type system for Rust, which does proper subtyping using first order predicates. Might be where it leads to, where you also do class sensitivities, so you can do safe casts into the type, and also the problem with different kinds of signatures depending on what outcome you're looking for.
Yep, should probably look into this. But yeah, we basically try to punt on everything until we get a standard library for it, because otherwise it's just so much scope creep that we can do that. Yeah.
Could you also use these ranges for floats?
Yeah, floats. So problem with floats is, what do you do if somebody specifies, well, I want my range to go from 1.0 to none, not a number. Then the compiler is like, okay, now I'm going to do none logic at compile time, and it quickly breaks down there because you cannot do the same behavior that you had at runtime. So if you copy the same logic to runtime to make sure your type is safe, you might not get the same result, because there's some subtle changes in there. Like if you did something from like 1 to 500 square root, that result might not be the same at runtime as compile time, and then you could get unsoundness because you're not actually in the range that you specified. So basically, we're just saying like floats, yeah, probably avoid them, allowing them in there at all, even though we allow them in normal patterns. Even in normal patterns, there's a bunch of lints that we had on them for a while. I'm not quite sure what the current status of them is. It's always a bit fishy. Yep.
Could you then translate float ranges to ranges of their integer representation?
Well, you can do that as a user, and then I don't know. I'm not sure what the question is. We allow you to basically do it, but then we in the background we kind of cheat and do something else.
So you would have to then store them as integer and just cast it to floats when you actually.
Right, but it would only work for like ranges that are actually in valid integer ranges. It wouldn't actually preserve the commas and stuff. I'm not sure. I mean, you could do fixed point math, for example. That would work. Yeah, we're not quite sure what to do when people are adding their own custom types in there and what's going to happen. But we're going to figure it out as we go. Okay, that slide took a lot longer than I expected. A lady of mine, constraints. So sometimes you want to do stuff at compile time. For example, we compute the start and end start starts and ends of pattern types, because those are constants, obviously. And you don't really want to use like just plain math and just simple functions. You actually want to use the traits that exist out there. For example, partial EQ, pretty useful for comparing things, or even just add of anything that isn't just a plain integer. And all these operations don't actually work in const evaluation land unless you turn on unstable features. And we're currently working on stabilizing them. So the current status is quite funny, because it used to be really simple. Now it's not simple anymore. So the thing is, you add a const in front of your trait. That allows that trait to be used in constant space. But all it actually does is allow you to write this kind of function. So what does this mean? So this function, these are normal functions. They don't do anything interesting. These functions are const events. You know const events, you declare them somewhere, and they're always const events, and they just keep working. And in this case, it means everybody that implements your trait also needs to provide a const event, even if the implementation of that trait is not meant to be used in const space. This is something we could just stabilize today. It doesn't actually have any complex questions around anything. And then there's this thing. You might have seen the old syntax, which was like a squiggly line const, and not actually in here in trait declarations, but the squiggly const was the thing we used to have. And now there was lots of discussions, and this is basically sometimes const, or like in plain text where you're talking about something and you put something in parentheses saying like, this is in parentheses very something. Yeah, it's kind of meant to be like that in a lexical way. I don't know. I don't really care. I just want the feature to work. So I just, whatever the Lang team comes up with, I'll accept it and merge it.
Maybe I missed it, but what is the semantic of putting it in place?
So when you have a actual function with your trait bound, you might want to use this, for example, in a constant block. And so what we had just now, oops, that was too far. This function, you can simply use in a constant block, because there's no requirement. Nope. There's no requirement on this trait, but it doesn't matter, because the function is declared as constant n. It must always be constant n. You could just call it here. That's fine. It gets interesting when this function is a constant n itself, because then you might not want this const here. You might just want to call t method in your constant n. And then the question becomes, how do you know this trait, the implementation for the concrete type that's going to put in here, has a const of n in the impl? And oh, I lost the slide. Anyway, so in the impl of our trait, we had our trait here. No. In the impl of this trait foo, this one you need to specify const. This one you cannot specify const. And this one you can specify as const or not, depending on whether you implement your trait as const. So you write impl const foo for my type, and then you need to specify this one as a const event and say this is always const now because it's in the impl, and this impl is always going to provide a const function for foo. For Bass is always going to do it anyway. Yes.
So this is sort of a const expr, non-const, const eval.
Yes.
Constructs.
Pretty much. Yes.
Okay.
It.
What if for some reason would need a constant and food? So both.
Oh, a constant event is always a normal function.
Oh,
They downgrade. There's another thing that we're not even talking about here, that there's no plans for adding to Rust yet, which is comp time fn, which would be a function you cannot call at runtime. You can only call it compile time. And those functions are actually pretty fancy, because you could have a comp-time function that allows you to add string literals together, and they produce another string literal, or do any kind of random kind of stuff like that. You basically could have an allocation function that instead of allocating memory on the heap because there's no heap at compile time, it would allocate a new static item. So you could have a for loop that just on compile time that just generates more statics as it goes. Totally fine, that would work. And actually, it works on this very, very bad nightly features right now, but yeah, they basically panic if you use them at runtime, so don't. We don't have comp time yet. Yeah, so this feature has a lot of more details. I could basically hold it and talk about that, but yeah, so we skip over that, but you can grab me later if you want to talk about it.
About 5 minutes ago, it showed it was
Oh, there's one? Okay, what's up? Cool. So generators. You might know generators from Python or other cool languages. In Rust, we don't have them yet. Well, we have them on nightly. We have had them on nightly since before we had async. Fun fact, async is basically just generators, but nice syntax around them for doing things. I'm going to explain more of that in a second. So generators are basically just ways to declare new iterators. We know empty, once, and repeat from standard library. They're an iter module, and right now they're declared by having a concrete type called empty that implements the iterator type, a concrete type called once that implements the iterator trait, and so on. But we could actually declare all of these on nightly today this way. A generator that is empty doesn't return anything. It just immediately finishes. It's basically the first time you call next, it returns a none. We'll get into how this works in a bit, but the once is a generator that yields one value. And after that, it finishes. So from then on, it will just keep returning none. And a repeat takes a value that's clonable, and it's just clones it and returns a clone every single time. So it will just keep returning the thing that you passed in. And basically, the way generators work are they generate this control flow graph of yield statements, where every time you hit a yield statement, basically the next function returns a sum value, and the whole generator keeps running until there's no more yield statements. Then it returns a none. And next slide, we're gonna see how this actually works if you have a more interesting generator. So this is a big generator. Starts here, ends here, and here. Initially, we do a for loop that yields a bunch of values. Then we yield one specific value, and then we yield values while some condition is there. This is similar to what you do with iterator combinators, where you're chaining an iterator with one single value chained to it, and then you're doing something like keep while or on that. But these are all behind each other. You can do arbitrary if conditions in here, which are like filtering out the elements. And you could put this entire thing in a loop. You could do arbitrary conditions. You can call functions. You can call other generators and yield their things. And this allows you to write more natural code than writing all these iterator combinators, because sometimes the iterator combinators are really, really painful. And in those cases, you don't want to use them. You usually want to use them because they're very pure and they allow you to know like where things are actually being mutated, where things are happening. But when you actually need all the control of where everything goes, when you have arbitrary random values somewhere that you want to yield, generators are going to make this really, really, really easy. It's similar to how before we had async, people wrote already async code with futures, but it was really painful because you had to use all these combinators. And this is basically the same thing. This is basically what async was for futures. This is generators are the thing for iterators. One sec. Oh, okay.
I can pass arguments to a generator. So if I put it in a function, I would use it as an
Generators are like
reusable chain.
generators are like closures. They capture values from this code. So if you put a generator from a function like once or repeat, you can move similar to how you move into closures a value, and then you can get the value. Yes.
Do a repeat example here. Isn't missing the loop?
It's missing a loop.
I was just
Yeah, sorry. There should be a loop around here. Yeah.
Is there a special syntax if you already have the iterator inside the generator to yield all items from the iterator until it is empty?
Yes, it's called for. Sorry. There was lots of discussion about this because Python has like this yield all thing. Yield from, yeah. But it turns out like just writing for loop isn't actually that much longer. If you're literally just like forwarding them. So for now, it's not that important, or we can just add a macro or something. Yeah, adding specific syntax for it so far hasn't been important enough.
Yeah, I think I know that's what yield and async can't interact with each other. You can't have a.
We have async gen. Oh, sorry. And then you can do both, and it'll figure out everything correctly. And then you get an async iterator out of that, which is an unstable trait that we don't know yet how to stabilize.
Would they be stabilized together, or is it once again a thing where like generators stabilize and I have to wait 2 more years until I can use them in async?
We're not sure if we're going to split it. We might just make them at the same time. Yeah, let's see.
We maybe bridge this somehow to stream of the view.
Yeah, basically async iterator is stream.
Yeah.
And we should probably rename it to stream because everybody knows what a stream is, but async iterator is like, yeah, maybe not.
But probably when you have an async gen, you probably won't be able to get a stream out of it, which is actually already standard, right?
No, stream could implement something to then later be implemented for all async iterator types. Something like that.
Okay.
So it's a one-time chance for stream. Once they do that, they can't go back. But like, there's no reason not to do it once it's stabilized. I mean, similar thing happened to the future trait. All the crates are not using the future trait from futures anymore, but have moved on to the future trait from the standard library. And something similar will happen. We're just not sure yet how to do it. And there's lots of fighting about how to do the details. So basically, any solution we pick will make somebody angry. So we'll see. Yes.
Is this using the same like enum style representation like futures are?
Yeah. Same thing, because everything actually is generators, everything is actually coroutines. So we had generators, the thing called generators, since before we had async, but we renamed it to coroutines and then added generators. Because what we actually had generators as arguments. So coroutines are basically closures, and those closures can yield. And because we don't have any good syntax for it, we add an attribute. So you slap the coroutine attribute on a closure or on a function, and now you can yield in the body of those. And that yield is a lot more powerful than the generated yield because the yield returns values now. And that's actually when you invoke a coroutine and you pass an argument in. The first time it goes through an argument, obviously, similar to closures. And from then on, it comes out of the yield. So the yield gives you an argument that is passed in the next time. The thing you yield is returned from the first call. And the next argument is then returned from the yield. So you're basically jump threading through these values. Yeah, that.
Can you explain again what the yield returns?
Say again?
What does the yield return?
So the first time we call the coroutine up there,
yeah,
we pass in hello. Hello goes into arg all the way in the top.
Yeah.
Then we walk down to the yield. Yield returns 43. So we get 43 out of this call. The second time we call this coroutine with cake, we don't start at the top. We start with the previous yield. And then that yield returns a value, which is the new argument that was passed in.
Yes.
Yes. And like in Python, you then have access to both the original argument and the new argument. And you can use both at the same time if you want to. And that's actually a problem. Because a lot of times you want to pass something in that doesn't survive the call. When you have closures, you can call them with an argument that has a lifetime, but like a reference something, but you don't want the closure to keep it around. You want the closure to call it once, pass it in, and then you want it to be gone. And then you next time you pass it in, you might want to pass it in again. You have this a lot when you have like context objects. You don't want the thing to capture your context object. You want your context object back. And so you want to keep calling this thing with the context object. Like that's what you usually want. You want to pass in a context object as your argument. For example, your database handle or something. You don't want to give the coroutine ownership of your database. You would just want to give it a short-term access to it. And then next time you could get it again, but in the current implementation, sadly, the first time you pass it in, well, that's it. It's gone now. And there is tricks that you can do. You can yield it and then pass it back in and so on. And that works, but it doesn't actually solve your lifetime issue because the compiler's like, yeah, but I still captured it. It's like I have the lifetime now. So this is just a limitation of the compiler right now. We need to fix that, but it's hard to fix.
So whenever I call the coroutine and pass in some maybe a moodref or something, the lifetimes.
The lifetime
Does the compiler know when the coroutine is at its end and then releases all of it?
Oh, at the end it knows it.
Okay.
But when you pass in the mutable reference, it acts as if that mutable reference is now mutably borrowed by coroutine until the coroutine finishes.
Okay, so the compiler knows when the coroutine finishes. But then does this the compiler call panic and not produce a compiler error because the compiler knows that the coroutine is
Well, the compiler knows the coroutine has been dropped.
yeah.
It doesn't know the coroutine has finished. Different concept.
But wouldn't the compiler know in the last line of the slide already that this would?
It's similar to iterators. Iterators at some point return none.
Okay.
Iterator's not gone. You can just keep calling next line. And technically you should keep getting nuns. But sometimes you get some spec out of it, which are bad iterators.
But the compiler knows after the line where it returns none that all of the moodrefs, for example, that I passed in can be.
No, it does not.
Okay.
You could actually
When it's dropped. Okay.
Yeah.
Now it's.
What are the types, and especially including the captured lifetimes across those different lines? Is there always the same type, or is it different type each coroutine invocation? Like
No, it's the same coroutine throughout the whole process.
and it's the same type.
It's the same type of coroutine.
If I pass in, like, what if I create a value, like between line 1 and 2, and
Yeah.
pass that value into line 2 instead of k? Like I create a value.
Yeah.
Like what is
The type needs to be the same. The argument type needs to always be the same.
sure. Argument type needs to be the same. Oh, okay. So and then also that's one.
There you go.
So I can't implement a like sequence type thing.
We are not in coroutines. No. That you need state machines for that.
Yeah, I was saying that. But and the second question, my limitation that like is the current behavior of the compiler that captures the value of standard, like until the end of the letter, is it an artifact of the fact that this was implemented for futures first, or and would we have futures? Like can we have at some point futures that don't capture until the end?
Yeah, I think that's with futures. It's not possible because they don't really have that concept. Like they have their weights to points, but you don't get information in. You always capture at the start with futures.
Right.
But with coroutines, you can change that. we don't know yet how we're gonna get all that worked out, but we will.
I was thinking about what the actual differences between the future and the coroutine in this sense. Because I think you could put a weight on something, like a function.
Yeah. Say crate out there, that's called generator. Where somebody implemented a macro around futures that allow you to write iterator impulse by writing async code that yield elements multiple times. So yeah, they're like completely.
So the reason you would also want this idea in the compiler is that the syntax.
The compiler doesn't need this feature. We cannot actually use this feature. We can use it in myriad things, but
Sorry, I think the reason you want it is part of the compiler, is part of the language.
oh yeah, because that's the only place where we can actually implement this like conveniently in the language and make it possible for you to pass in different arguments and not have to capture them all the way. Like the thing I mentioned earlier, when you pass in something with a lifetime, a mutable reference or something, you get to capture forever. Only we can fix that. This cannot be fixed in user code.
I have to think about it.
Yeah.
Put an argument in the coroutine. Looks a lot like the generator.
Yeah.
Why do we have two different syntaxes? Basically, that's more powerful. Why doing generators?
Because then changing something very small, like adding an argument to disclosure, suddenly makes it not implement iterator anymore. And that would be kind of weird, like if such a small change changes whether it implements iterator or not. So we're basically adding explicit syntax when you're changing the traits that are implemented. Not big change. Negative impulse. Do you ever want to say that your type is actually not absolutely not going to implement this specific trait? You sometimes do this. You sometimes do this for sentencing, where you're like, this type is never going to implement same. Please don't implement same for it. That's bad. And there's ways to do that. There's ways to do that where you're just adding like raw pointers and so on to your type to make it not be sent anymore. Those schemes are obviously not great. So negative impulse. You can implement not debug for your type. That means you're making a promise. You're making a promise to your users that you're not actually ever going to implement debug first. And this promise is actually really useful because then when somebody implements a wrapper type, and for the wrapper type implements debug for all types that implement debug, you know, oh wait, my type does not implement debug. So even though you have this blanket in here, you can now implement debug for the wrapper type of my type. And this actually works completely fine. Well, it doesn't actually work yet. But this is the minimal thing we want to do before we stabilize them, because it's really, really useful to have this kind of feature. It avoids a lot of problems that you have sometimes called with the orphan rules, if you've ever encountered them. And this allows you to work around a bunch of these issues that are there, because sometimes they are like over-eagerly triggering for things that you don't actually want to trigger on. For example, we know F32 is never going to implement ORD. It's only going to implement partial ORD, so you can compare it, but you know it's not absolute ordering. And if we add a negative impulse for that, that's going to be useful for implementers, because then they can implement something for all types of the ORD, and they can implement it for F32. Yes.
I just remembered why I always wanted this. Because this is kind of hypothetical. I always thought would it be great if there were blanket inputs from and into that implemented the transitivity. But then I always thought that can't work if you want to also have the direct part. But with this, And then you could add blanket implement for transitivity for from and into a try from, and then still implement the shortcuts if you know a more efficient conversion. But you
I'm
know,
not sure that's going to work because blanket implements aren't set library. They're not in your code.
okay.
And you're probably still going to run afoul of the open rules there. But there's probably something here that we can improve. I mean, it's a common issue that from is always implemented for the type itself when you actually like that's a common problem that you encounter when you implement your own from impulse generically. So yeah, we would like to improve this, but I think that's a slightly different issue that we haven't figured out yet. Quick step to trade aliases. I think then we're almost done. Trade aliases are really fun because they're basically the same thing as for type aliases. You just are allowed to like have a new name for a trait and just stick all your traits in there. It's easy if you have done and only have duns because then you do like type foo equals done debug plus display or something. But if you don't have that, if you're actually limited to generic types, then you need trait aliases. And one cool thing that is being intended for these is I think they're basically blocked on allowing you to implement the trait alias. So the language basically wants you to be able to write impl foo for my type, and that implements both debug and display at the same time. And of course, there's problems because both debug and display have an FMT method, and so there's a name collision there. And figuring all these details does take a lot of time, so that's why we don't have trait aliases. And the problem is we can't really stabilize them at this point because then we're gonna take away a few things that we can't do that anymore later. Yes.
Can trait aliases also generic parameters?
Yes. Yeah. But, yeah. Yes. You can basically fake them today, but it doesn't work quite the same way. It doesn't ring the same way. It has a few problems that don't appear the same way. If you are in need of them, you can usually use this trick where you have a new trait that requires your types, and you just implement it for all T that implement those basic types. I have this an every second crate that I write. I have something like this because I always need it for something. Yeah. It does have more problems than trait aliases, so use it sparingly for specific issues or just for private traits. Putting it in public interfaces is mostly not useful. Oh, I lied. There's one more. Try blocks. Try blocks allow you to use the question mark operator functions that allow returning options or results. And it's really cool because you open the try block, call some function that returns an option. It's the question mark away, do something with the result, and then you just finish this block and you still get an option out of it. And then you can unwrap for this option or you can pass somewhere else. But this allows you also to use the question mark operator for options inside code that actually returning results and so on. Like you can do better in the mixing, and you can then combine all of these obviously with like generators, saying you get the combinatorial explosion and you get cool things out of that. Yes.
When will this be step?
We'll finish generators first. Wait, I lied again. Sometimes this is a very common pattern. You write visitors, and your visitor has a visit thingy, and then you have a walk thingy because somebody implementing your visit thingy function might have like conditions. Oh, if it's that variant of thingy, I want to do something special. Otherwise, just always do the normal default thing. And here's the function that is the default thing. And this pattern happens like a billion times. And I don't know if it's just compiler brain because we have like, I don't know, 500 of these in the compiler. Like, I'm not even joking. But you can just do this now. You reuse the walk thingy as visit thingy. and it'll just do the thing for you. And yeah.
What is it? Yeah, maybe explain it.
So this produces the exact code we had earlier. It generates a visit thingy function that has the same signature as this one, except it'll figure out that this is actually n self or something. And then it actually invokes the body too. But you only need to declare this once. You don't need to do the forwarding yourself. And it gets much more cooler because this isn't just for use in this situation. You can also use this to move functions out of trait impulse into the global space or inherent impulse. Move free functions into inherent impulse. Like you can move everything around and do funny things like this, where you're not importing the vector length function. You're reusing it, putting it in your own namespace. It's now your function. You own it, and you can now use Python style len. Not sure if it's useful, but it's funny.
So you don't have to call function inside your function.
Yeah.
But does it still call the function
Yes.
inside your function?
Yes.
The curves?
Yes.
Yeah, but then you still get these overhead.
No, it's just inline. Like this is like trivial inlining. Because like the compiler will do the right thing in this case.
Okay.
Like this is so that simple. Like yeah, this one the compiler's gonna figure out all base. It's just sugar.
Great sugar.
Thanks.
Somewhere where I think this might be really useful is actually in streams and sinks, where the top of your user crate uses framed read and framed write, and that will yield you streams and sinks. But you usually want to expose your framed types to the public API, so you wrap them in and out of type, and you're saying that I could. But how can you reuse the trait? Can I use this within a class to call the functions from the inner type?
We don't have classes.
Structs.
Well, you can use it in a struct, but you can use it in a import block for a struct.
I think that's what I want. Yes.
Yes.
I think it is.
Yes, that works. That should work. But bleeding edge, the diagnostics are pretty bad, but it's actually working pretty well as far as I can tell. And I think it's actually, somebody tried to use it in the compiler recently.
I feel that you use up this reuse keyword for a very specific thing and you might regret it later.
This might not actually be found sometimes.
Okay.
That's what it's. That's right. I didn't expect to stay on the short slides so earlier. I should have expected that, I guess. So you have a struct, it's generic, and we have a value of that struct. For the non-generic thing, we pick a value. For the generic thing, we pick a string. And then we use struct update syntax, and we update the B, but it's a different type. Completely different type. And this just works on that thing. Just fine. It has been working for forever. I don't even know why we couldn't stabilize it yet. I will have to check. I think this one just got lost, literally. It takes the 42, just like normal struct update syntax. It does this with all the fields that you didn't specify. So you can have multiple generic parameters, and it will keep those that you didn't specify, and it will change those that you did specify. Yeah, I could have used this so many times as we made it.
I don't.
Sorry, I didn't understand it. You don't think it increases readability? Ah. Well, I think the main thing it was motivated from was like this whole like when you're building up a struct and you start out like keeping everything like empty tuples or something like that, and you're slowly building it up instead of like having to build it up all things at once. And then you can just keep the previous values and just add the new ones to it. Yeah, this is a fairly niche feature, but it's also very hard to use wrong. So it doesn't really, there's no real danger to it.
Will it also work for all the other values of A? I mean,
Yeah.
Oh, okay.
It will move all the values of x. Yeah, only the ones that you're overriding, those it will change, but everything else just stays the same. It's not immutable. Yeah.
Just I wrote too much text for this. This is all of the pen spread syntax we need.
Well, the dot has a comma at the end, but otherwise there's no order.
It always has to come.
Yeah. Async functions and traits. We had that. Wait, there's async function and traits. You might know the async trait function from Ditone. And the problem with it, the async function here is always boxed. So the future that return from it is always boxed. And always boxing means that there's overhead, especially because it's now very hard to inline it. And then there's all other kinds of problems. And so the idea is to simply allow the syntax to work. So right now, you cannot use this because foo is not bit safe because there's an async function in it. And the idea is that we're going to use that. And right now, it's a little bit hacky. We're not going to stabilize the version because it just boxes the thing and it just literally requires box to exist. So on embedded devices where you're using no std, you just can't do that. And there's all kinds of problems with that. And people might want to use reference counting or might want to actually just store it in a local variable or something like that. There's different things that we're going to do. So we're going to improve on this. But basically, yeah, we kind of know how to get this done, and we're just hacking away on it until it's done, and it's going to come. Oh, finally, the end. Super lit. Very, very, very bleeding edge feature, but it was very short to implement, and it didn't have any bugs. That was weird. So sometimes you have a function that where you do a match, and you want to return the value from that option. And this option returns, for example, a reference. And in the else case, you don't have any value. There's none. So what do you return? What you can do is you can create a local variable outside of the scope, assign to it, and then return a reference actually to the x. Sorry, that should be x. And then you have in there a reference. You don't know how long it lives. It lives a little bit shorter than this thing, but it lives at least as long as this one. And you can access that. But that's a lot of going back and forth and having to remember that x belongs to that one. Yes, this works. Assigning later, not without mutability, that's all fine. But now you can literally just say super let because super is a super keyword. And this will move the let itself out of one scope. And
Can I change?
no, you cannot use multiple supers. But
I think that really should have for
but the thing is, we had the super keyword. Could use it in this position without breaking anybody. So yeah, but super duper would work. So this feature is actually pretty funny because if you use this in a static initializer, like in the body of the static initialization, the super scope is like the static scope. They're just generating more statics. So your local variables that are super let are actually new statics that you're declaring because they outlive your static, which already lives for the static lifetime. So they also live for the static lifetime. Yes.
Can I use this on the top level scope of a closure?
To declare a function in the outside. I don't think that works. I think it's our closures and functions. What it currently does, but what we might actually just change in an error. What it currently does, it creates a variable that lives the longest in the body. So normally when you declare variables, they are declared in order and they are dropped in reverse order. But a superlet will be put all the way in front of all of theirs. Yeah, we haven't quite figured out what to do with them in that scope.
If I have multiple superlets, which one goes first?
Those are going to go against.
Can this be used to get rid of the extra int level when I like need to clone something into an async job?
No, that's a different feature that I don't have any slides for today, but I'm happy to talk about.
So and the other thing, I don't know I guess it's the lexical scope. I don't know, like like what variables can I use in place of the 12? Like if I want to put an expression in place of where the 12 is,
Yeah.
can I use like only variables? I use variables that are in my
Anything that is available here.
It's a declaration.
If you can name it, it's just the assignment, basically. The super only changes where the memory is placed. It doesn't change anything about the assignment.
So what is the advantage of placing the left or the left side?
You mean, oops, that one?
Yes.
This is the same thing.
So why do you want to have that keyword? Have that extra feature in the language?
Well, it does this, but it also, if you have temporaries inside the assignment and you're declaring this at the top level, for example, those temporaries live for the body then. Sometimes it will be when you get a lifetime error, the compiler will just tell you add super in front of it and then in front of the let binding and everything will just work. You frequently have this when you're having a long expression that has, for example, a guard inside. When you're doing mutex lock, unwrap, access field, do something, and so on. When you do this long chain, some compilers sometimes tell you please split it up into multiple variables. But if you change the initial thing to super let, it'll do that automatically for you. That obviously has its own problems because the locking scope gets longer, but you explicitly ask for it. So
basically, it's there to make the error message or the fixed message a little bit shorter.
Yeah, it's also the change that you have to do because sometimes, like if you declare a variable just to only use it once, you should be allowed to just write it all the way out, and this is basically the fix for it. Yep.
In your subjective opinion, does it really work to use up a keyword for such a feature?
Well, it doesn't. The keyword isn't used up because you couldn't use it for anything else here.
Yeah, not free to choose for a different feature in the future.
Yeah, but for a different location, you can still use it. I mean, the super keyword isn't burned up. It's just used in front of let binding. So statements can't start with super let. Like it's literally a super let combination that is burned. And super if actually would still work.
What if it is super else? We are piling on a lot of features.
Oh yeah.
In this language. So is there not just some way when if it's really worth to add in the next feature?
Well, this one is actually immensely practical inside macros. Because, for example, the pin macro and a bunch of other macros that declare new variables, but want them actually stored somewhere outside, they can now do this with superlet because they can actually escape their own scope. And previously they couldn't. So this is actually a fundamental change and something you can do, but we don't actually need it for anything else. Like we could hide this completely in a macro to allow you to do that. We wouldn't have to burn the syntax, but at the same time, the syntax is not that surprising. So maybe we're just gonna use this.
We're getting really right. So that means that the lex is always there. It does not matter. It doesn't matter whether there is.
It's always there outside. One scope outside. So it's the same scope as let y.
Yes. And when I put it really inside after the foo, like function foo, if I write super let there, is there a scope outside?
Yeah, that we're not sure. We're probably going to turn out error, but for now there is a scope, which is just before all the let bindings.
Oh, okay. Version scope.
Yeah, that scope actually exists in the compiler since forever because arguments live there.
Okay.
So you're moving it to where the arguments live, which is semantics, but it's actually a thing the compiler has. So that's why that's one of the reasons the feature just accidentally worked everywhere when it was implemented. Like,
But wait, you can maybe structuring inside of the parameter definition. What is actually by super there?
no, you can't because that's not super let. It's literally super let.
Yes.
You cannot use super. There's no let inside the arguments.
Oh, yeah. Oh, yeah.
I didn't study computer science, so perhaps I'm mixing some things up here, but the macro rules thing was kind of hygienic. And wouldn't that break a hygienic?
No, it's still hygienic. Yeah, because
hygienic.
hygienic. hygiene only means that you cannot access names from outside the scope unless you're declared within that scope.
It's very clear for that,
Yes.
but you as the user, as the macro can't.
No, that the variable isn't there. It's you're only changing the where this thing is stored.
Yeah.